This conference will now be recorded.
Good morning, students, and we'll continue with our introduction to absorption spectroscopy, where we left off in the last class. So last class we last discussed about the different shifts seen in absorption spectroscopy. The shifts seen in the absorption spectra that we observe in absorption spectroscopy. And they were bathochromic shift, that is also known as the red shift, which is a shift in absorption to the longer wavelength or lower wave number or lesser energy also. So this is a shift in the absorption peak. We have also seen what's an absorption spectrum. It's a plot of the absorbance versus the wavelength, or it could be a plot of percentage transmittance versus the wavelength, or percentage transmittance versus wave number. So on the y-axis of the plot, you could have either absorbance, percentage transmittance, or transmittance, or log absorbance. Whereas on the x-axis, we could have either the wavelength, frequency, or wave number. That is what is absorption spectrum. Now, in this absorption spectrum, for a given compound, you could get a Gaussian shaped peak. And that peak may undergo a shift in the position to a longer wavelength or a lower wave number or lower frequency, whatever is there on the x-axis. This type of shift is called bathochromic shift. Why it occurs, we will subsequently see. One example is when an oxochrome attaches to a chromophore. The chromophores we have already seen. One example is the benzene ring itself, the phenyl nucleus, and the oxochrome. If OH attaches to benzene, what do you get? You get phenol. So once benzene is changed to the phenol structure, we will see that the absorption spectrum actually shifts to longer wavelength. That means the molecule undergoes a bathochromic shift or a red shift because of the oxochrome OH attaching to the benzene ring. Hope that is clear. The second type of shift is called the hypsochromic shift. This is also called the blue shift because this indicates a shift in absorption to shorter wavelength or higher wave number. So shift in absorption to a shorter wavelength or higher wave number. So this is the opposite of bathochromic shift. Now you can make out why we have called this the blue shift. The blue shift because blue is a shorter wavelength color and red is the longest wavelength color. This is with respect to visible light. So we can always visualize the visible light. You have the Vibgyor colors with red on one end and violet on the other, violet and blue. So blue is a shorter wavelength, red is a longer wavelength. So whenever the shift takes place to longer wavelength, we call it a red shift or bathochromic shift. When the shift in absorption takes place to a shorter wavelength or a higher wave number, we call it blue shift or hypsochromic shift. So how this is caused? Just by the opposite, for the opposite reason as the bathochromic shift. Suppose an oxochrome is removed from a chromophore, an oxochrome that was potentiating the intensity of absorption of the chromophore. If that is removed, then you see a shift in the absorption to shorter wavelength. We will see some examples later on in later coming up slides. Then you have another shift which is also called the hyperchromic shift. This is increase in intensity of an absorption band. And hypochromic shift, that indicates a decrease in intensity of an absorption peak. So you have hyperchromic, where you have the same absorption peak, it increases in height, and hypochromic, it decreases in height. This will become more clear from this picture. Here you have, this is the spectrum, absorbance versus wavelength. This is particularly for UV visible regions of the electromagnetic spectrum. Now you see the peak is the light green colored in the center. That is the actual peak. Whenever there is a bathochromic shift, this green peak will shift towards the orange. So now this green peak will not appear, an orange peak will appear. Say, for example, when OH attaches to the benzene ring, then you see a bathochromic shift. Similarly, if you have a hypsochromic shift, instead of this green peak, light green peak, you get the blue peak. That is, it has shifted to shorter wavelengths. What is hyperchromic effect? You see the dark green peak. So there is an increase in intensity of the absorption. Then this also happens in certain cases. We will see those examples. And sometimes there is a decrease in the absorption of the absorption peak, intensity of absorption peak. That is hypsochromic shift, the white one. So here we see the different types of shifts that happen. If the peak shifts to the right, to longer wavelengths, it's called bathochromic shift. If the peak shifts to left, that is shorter wavelengths, it's called hypsochromic shift. If the peak increases in height or intensity, it's called hyperchromic effect. And if it decreases in height or intensity, it's called the hypochromic effect. So in detail, we'll see each one of these. The bathochromic shift, I mentioned a little about it. It's a shift where the absorption is shifted towards longer wavelength. It's also called the red shift. And how can it happen? It can happen when there is a change of solvent. That is mainly the polarity of the solvent is going to change, then it could lead to bathochromic shift. Or when an oxochrome is attached, then also it could lead to a bathochromic shift. And one more possibility is when there is an increase in the degree of conjugation. When there is increased conjugation, then also you can see a bathochromic shift. Now, we have already discussed about the different types of transitions. You have the n-pi star transitions and the pi-pi star transitions, mainly occurring in the UV visible regions of the electromagnetic spectrum. Out of these, the n-pi star transition for carbonyl compounds, which type of compounds will show? Those which have the n electrons. So carbonyl has CO group and therefore n electrons will be present. So for carbonyl compounds, you will get an n-pi star transition. You will also get a pi-pi star transition. Okay, the n-pi star transition will experience a bathochromic shift when the polarity of the solvent is decreased. And it will be the opposite effect for the pi-pi star transitions. When the solvent polarity is increased, then pi-pi star transition will undergo a bathochromic shift. The n-pi star and the pi-pi star have opposite type of shifts with the same change in the solvent polarity. So if solvent polarity is decreased, that means you make the solvent more nonpolar, in which you have dissolved the substance, then you will see the n-pi star transition band undergoing a bathochromic shift. If you make the solvent more polar, then you will see the pi-pi star transition band undergoing a bathochromic shift. Then I also mentioned about degree of conjugation. Yes, now you have benzene, which absorbs in the UV region. You have one more ring, that is, the naphthalene structure, 2 rings, fused rings. So that absorbs at longer wavelength compared to benzene, which absorbs around the 200 to 270 nanometers. Naphthalene is at still longer wavelengths, but in UV region, the color of naphthalene, it's white, so you get a colorless solution. But as you go on increasing the number of rings, when you make it tetracene and pentacene, that is 4 rings fused together, 5 rings fused together, you will see that these substances, pentacene, they are going to absorb in the visible region, and they are colored compounds. So that's how we can say that increasing the degree of conjugation also causes a shift in absorption to longer wavelengths, or in other words, a bathochromic shift. The second type of shift is the hypsochromic shift or effect. This is a shift to a shorter wavelength. We just saw that. It's also called the blue shift, and change of solvent towards higher polarity or removal of conjugation will bring about this type of shift. So exactly opposite to what happens in pathochromic shift. So change of solvent, again, now this will vary for the N-pi star transition and the pi-pi star transition, exactly opposite to what happened in the bathochromic. So now there in the bathochromic shift, we were getting a bathochromic shift for N-pi star transition if the solvent polarity was decreased. So here for the same N-pi star transition, we get a hypsochromic shift if the solvent polarity is increased. On decrease, you get a bathochromic shift. On increase, you get a hypsochromic shift. This is for N-pi star transition. However, for pi-pi star transition, you get a bathochromic shift with increase in polarity and a hypsochromic shift with decrease in polarity. Hope that is clear. Aniline, this is an example. Aniline, 280 nanometers. This is the absorption peak. It's a conjugation of pair of electrons of nitrogen with benzene ring. So there is a slight shift. Aniline has NH2 group attached to the benzene ring. In acidic solution, it will form NH3 plus due to removal of conjugation or removal of lone pair of electrons. So hence the absorption takes place at shorter wavelengths. It is 203 nanometer, and this is called hypsochromic shift. So you get a hypsochromic shift in acidic solutions. What it's doing is it's removing the lone pair of electrons. So N electrons are not there. In that case, it removes the conjugation also due to removal of conjugation and or removal of lone pair of electrons. You will see a shift towards shorter wavelength. This is one example. Then we come to the next effect, that's hyperchromic effect. It is a shift due to increase in intensity. So the epsilon max value increases. What is epsilon? It is molar absorptivity, and it is a measure of the probability of the transition taking place. It's the measure of the intensity of the absorption that is going to take place, and it represents the fraction of radiation that is absorbed. So more the absorption, greater the epsilon value. And epsilon max is the highest absorption value. So due to the introduction of oxochrome, you could get a hyperchromic effect. So we have already seen that when you introduce an oxochrome to, close to a chromophore, you get a bathochromic shift. And here we are seeing that when you introduce an oxochrome close to a chromophore, you may also get a hyperchromic effect. Both are true, and that is why on introduction of an oxochrome close to a chromophore, you get usually two shifts. Both are seen in most cases. That is, you get a bathochromic shift with a hyperchromic effect. For example, pyridine. 257 nanometers and epsilon, this is the lambda max or the wavelength of maximum absorption, and epsilon max is 2750, 2750. Now you introduce the methyl group, 2-methyl pyridine. So you're introducing the oxochrome, that is the methyl group. So what happens to the lambda max? It is shifting to longer wavelengths. From 257 nanometer, it is now shifted to 262 nanometers. So there's a bathochromic shift. And also observe the epsilon max from 2750, it has increased to 3560. There's an increase in the intensity of absorption. Hence, we say there is also a hyperchromic effect. Another example is Benzene shows B band, the secondary band in UV visible spectra at 256 nanometer and with an epsilon max of 200. Whereas aniline, because in aniline, same thing, in aniline, NH2 is the oxochrome that is introduced. So on introduction of oxochrome, you get aniline. This shows a B band at 280 nanometer. You can compare these two, 256 to 280, so a bathochromic shift. And also aniline's B band has an epsilon max at 1430. From 200, it has come to 1430. So there is a hyperchromic effect. The increase in value of epsilon max is due to the hyperchromic effect of oxochrome NH2 getting attached to the benzene ring. I hope it's clear now. What is hyperchromic effect? And the last type of effect is the hypochromic shift. This is inverse of hyperchromic shift. That is, there is a decrease of intensity of absorbance. Introduction of any group to the compound, which is going to alter the molecular pattern of the compound, results in hypochromic shifts. Introduction of any group to the compound, which is going to alter the molecular pattern of the compound, results in hypochromic shift. You can see an example. I have given an example here. You have biphenyl. This is first top of structure is biphenyl. It shows lambda max at 250 nanometers and epsilon max at 19,000. Okay, so a very high absorbance and a lambda max in the UV region. Now, when you have 2-methyl, this is the oxochrome getting attached to the structure. You have 2-methyl biphenyl now. So when an oxochrome attaches, like methyl, what is happening to it? The decrease in value of absorbance is due to hypochromic effect of methyl group, which distorts the chromophore by forcing the rings out of coplanarity, resulting in the loss of conjugation. So this is a different type of effect. We saw earlier that an oxochrome generally causes a hyperchromic effect. But here, because the whole molecular pattern of the compound is disturbed, the chromophore itself is going to get distorted because of loss of conjugation. The double bonds are going to shift, and because of this, you will see a hypochromic effect. So this is also one example of hypochromic effect. Other cases, you can also say whenever hypsochromic shift takes place, then it is generally also accompanied by a hypochromic effect. Now we come to another important, some important terms. These are some basic terms that you will see in any spectroscopy. Transmittance. It is a measure of the quantity of radiation that is transmitted by the solution. It is a measure of the quantity of radiation transmitted by the solution, or in other words, it's a measure of the quantity of radiation that's not absorbed. You can see in this picture, it's an attenuation of a beam of radiation by an absorbing solution. Here, this is the incident radiation. It is passing through a solution of concentration C. This solution is capable of absorbing this particular wavelength of radiation. That's why we call it an absorbing solution of concentration C. Now you can see the intensity of the incident radiation, IO, is of particular value as indicated by the width of this arrow. Next, we see that some radiation may get absorbed by the solution here and the remainder gets transmitted. If there is absorption, remainder is always less than what was incident, and that's why it's been shown with a narrower arrow compared to the incident arrow. So this is more narrower. So transmitted radiation is becomes less in intensity if there is some absorption taking place in the solution. So it's a measure of the quantity of radiation that is not absorbed. What is absorbed is removed and the remainder is transmitted. So transmittance intensity of transmitted radiation T or transmittance T equals I by IO. What is I? I is the intensity of transmitted radiation and IO is the intensity of incident radiation. Sometimes we also use, instead of I, we also use the term I subscript T, IT, very clearly indicating that it's the transmitted intensity. So if you define it, you can say fraction of incident radiation transmitted by the solution. That's transmittance, T. What is absorbance? More commonly encountered term is absorbance, and it is the logarithm of 1 by T. Because you see, A equals log I0 by IO by IT. What is T? Capital T? Capital T is I by IO. So if you invert this, you get 1 by T, and absorbance equals log 1 by T. Okay, or in other words, negative log of T. So absorbance actually is negative logarithm of transmittance. So when absorbance increases with increased attenuation, at the same time, you will see that transmittance will decrease. More the absorption, absorbance values will become high, but more the absorption, transmittance will start decreasing. Attenuation here refers to absorption which is occurring, because we are talking about absorption phenomena. If it is, we are talking about scattering, then it would be attenuation would refer to scattering. Here we are talking about absorption spectroscopy, so attenuation refers to absorption by the sample solution. So when more absorption takes place, absorbance A will increase. At the same time, transmittance T will decrease. Now we come to another term called lambda max. Lambda, we already saw, is the symbol used to denote wavelength. So the symbol used to denote wavelength is lambda. And what is lambda max? Lambda with a subscript max. It is the wavelength at which absorbance is maximum, or absorption maximum is the wavelength of maximum absorption. The common mistake that is done by students is you call this is the maximum wavelength of absorption. That is totally wrong. The correct way to define absorption maximum or lambda max is, it is the wavelength of maximum absorption. It's not the maximum wavelength. So be very careful when you define lambda max. Wavelength of maximum absorption. This is a UV visible absorption spectrum for bromothymol blue. You can see there are two peaks. So which is the wavelength of maximum absorption? Here you see the highest peak. So you will draw a vertically straight line to the x-axis and you can find out what is the lambda max for this particular compound. It will be somewhere in this region. What is the significance of lambda max? It is useful for identification of samples, as lambda max is characteristic of a sample. So in a given solvent, you will get a particular lambda max for a given sample. So it could be used for identification of samples. UV absorption spectroscopy is not a very good tool for identification, but it could be used at the primary stage. It is quite good, not very accurate. So if it is being used for identification, what we look for is the lambda max. We try to match the lambda max of our compound with the standard compounds. Also, lambda max has got some significance in quantitative measurements. Quantitative measurements, I know you all understand. It means to find out how much of a particular substance is present in a solution, that is to quantify the solution. So lambda max is also preferably used as the wavelength for quantitative measurements in absorption spectroscopy with UV visible radiation. When we are doing quantitative measurements, we will not be bearing the wavelength. We will generally be using a single wavelength, or in other words, a monochromatic beam of radiation. So which wavelength to choose? That is preferably the lambda max of the compound we are trying to analyze. And why do we use preferably the lambda max for quantitative measurements? There are two reasons for that. One is the lambda max, if you're working at the lambda max, you get maximum sensitivity. Because as you know, you'll see the graph here, at lambda max, at this wavelength, you will see that this substance gives you the maximum absorbance. Suppose you reduce the concentration of this substance. What happens to this spectrum? This spectrum, say you make the concentration of the original solution half. What happens to the spectrum? This peak will come half. This will also come half. So the absorbance, maximum absorbance will now become this. But the wavelength of maximum absorbance will still remain the same. So lambda max will not change with concentration, but the absorbance value will change. Okay, epsilon max or will change for a given, depending on the concentration. If you make the concentration again 1/4, again you see a decrease. So like this, if you go on decreasing the concentration, as seen in solutions where you have very low concentration, then what happens? You will see that at other wavelengths, there is no peak at all. There is no absorbance. There is zero absorbance. Only at the lambda max, you will see a very small peak. If you can see a small peak, that means you can still make the measurement. That means even such a low concentration, which cannot be determined at any of these other wavelengths, can be determined at the lambda max. If you're using lambda max as the wavelength. So this is what I meant here, because sensitivity refers to how low a concentration can be measured accurately. So you get more sensitivity if you work at lambda max. Or in other words, you can measure smaller concentrations if you work at lambda max rather than other wavelengths. Secondly, in quantitative analysis, we use lambda max preferably because minimum errors in absorbance occurs even when there are errors in wavelength setting. When you have errors in wavelength setting, say instead of 220, you are putting 221, it is a very small error. But if you are working at the lambda max, there is very less change in absorbance because it's a broadband spectrum. When you have a broadband spectrum, near the lambda max, the change is less. But away from the lambda max, because of the slope on either side of the lambda max, you will see bigger changes in absorbance with small changes in wavelength setting. So I hope that is clear. What is the significance of lambda max in quantitative measurements? Then you have another term called absorptivity. It is denoted by small a. It is the ratio of absorbance of a solution to the product of its concentration in grams per liter and path length. So you see here small a equals absorbance divided by BC. So BC is R in the denominator, A divided by BC. So B is the path length in centimeters and C is the concentration in grams per liter. A is of course the absorbance of solution. If you take this ratio, you will get the absorptivity. Absorptivity is also a characteristic of a substance, but it's dependent upon the concentration and the volume of the solution. Molar absorptivity, epsilon, is the absorbance of a 1 molar solution through 1 centimeter. Fixing the path length as 1 centimeter and the concentration as 1 molar, then whatever absorbance you are measuring, that is the molar absorptivity. Molar absorptivity is a very good characteristic of a substance, so it can be used to compare two substances. So it can be used to compare two substances. And then you also have one more term which is called specific absorbance. Specific absorbance is denoted by E 1%, 1 centimeter. 1% is the superscript, 1 centimeter would be the subscript. This refers to the absorbance of a 1% weight by volume solution through 1 centimeter path length. So you have a 1% weight by volume solution, that is 1 gram in 100 ml solution, and you have the path length of 1 centimeter. That is, the solution is contained in a cell which has a length of 1 centimeter through which radiation is going to pass. Then the absorbance measured would be called the specific absorbance. So this is another term that is used in spectroscopic studies. So now we come to the types of chromophores and their effect on spectrum. You have seen what are chromophores, and they are the groups that are responsible for, absorption. And you could have different types of chromophores, and do they produce any effect on the spectrum? That is what we will be seeing now. So the first type of chromophore is the isolated chromophore. What are isolated chromophores? Now, before we see this, we have seen, say, for example, a substance is capable of absorbing a given wave region of electromagnetic spectrum. So you will get a peak for that substance with a lambda max, and the highest point will give you the epsilon max value also. Now, when you have two chromophores, how do they behave? Do they produce any effect on the spectrum of the compound? They actually produce an independent and additive effect. And you will see the epsilon max value increasing. We'll take an example. This is the compound Ca3CH2CNS, where the chromophore is the CNS group. And for this compound, you will get a spectrum with a lambda max of 235 nanometers and an epsilon max of 800. Now, we are going to take another compound which is two CNS groups. And what are isolated chromophores? They are two chromophores that are separated by at least two single bonds. It could be more, it should not be less. So you have two chromophores separated by at least two single bonds, and they are called isolated chromophores. So here in this compound, you have the two chromophores, both are the same chromophore, and they are separated by more than two single bonds. So 1, 2, 3, 4. So you have two isolated chromophores. Now, if you see the spectrum of this compound, you will see 7 and the epsilon max at 2000. There is not much change in the lambda max because the groups are the same. That's why it remains at 237. This is considered almost the same. But there is a huge difference in the epsilon max value. Epsilon max signifies the intensity of absorption. And therefore, you can here see, because you have two similar chromophores compared to the first molecule, you have more than double the epsilon max. That is why it was told it is additive. It is independent because each of these absorbs at around 235 nanometer, and that's why the peak is obtained at 235 only. But their effect is additive, so each produces 800 plus 800 like that, and that's why approximately it comes to 2000 epsilon max, a little over double the intensity. So this is the effect that is produced by isolated chromophores. Next, you have conjugated chromophores. So conjugated chromophores means chromophores that are separated by only one single bond. So you all know what is conjugations. So the way you have, say, two double bonds separated by one single bond, then you will say the two double bonds are conjugated. Now, conjugated chromophores, what is the effect they produce? So if you are increasing the number of conjugated chromophores, you will always see a bathochromic shift with a hyperchromic effect. So the intensity will increase and the absorption peak will shift to longer wavelengths. Why does this happen? Now, conjugated chromophores means two double bonds separated by one single bond. In double bonds, you have the pi electrons, which are residing in the pi orbitals. When you have two double bonds separated by only one single bond, you will see overlapping of the pi orbitals. And subsequently, there is a decrease in the gap between the pi orbitals. So between pi to pi star, the gap will reduce because you have overlapping pi orbitals. And when the gap reduces, the energy required for a transition will be lesser. If the energy required is lesser, then the wavelength of radiation required will be longer. And that is nothing but bathochromic shift. And that's why we see a bathochromic shift in case of conjugated chromophores. And like I told you before, bathochromic shift is usually also accompanied by a hyperchromic effect. So more the conjugation, more the intensity of absorption. Then the third type of chromophore are seen in the aromatic compounds. In the aromatic compounds, if you have extra substituents being added, what they have different types of effects. Certain substituents, they cause an increase in absorption, and certain substituents may not produce much change in absorption also. Degree of conjugation, I have already mentioned with the example of benzene, naphthalene, tetracene, anthracene, pentacene, like this. If you go on increasing the conjugation from one one ring to two rings, two to three, three to four, four to five, you will see again a bathochromic shift with a hyperchromic effect. So these are some effects that we see with different types of chromophores. So to summarize the various terms that we have studied today, the terms that are employed in absorption spectroscopy, the first column indicates the term and the symbol used. The last column indicates the alternative name and the symbol for the same term. And the center column indicates the definition or the equation to determine that particular symbol or that particular term. So first term is incident radiant power, is also called incident intensity, incident radiation intensity or incident intensity. If it is referred to as power, then it is PO, and if it is referred to as intensity, we represent by the symbol IO. So it is the radiant power in watts in incident, which is incident on sample. Radiant power in watts, incident on sample. Second term is transmitted radiant power, designated by the symbol capital P. or it could be called the transmitted intensity, designated by capital I or even I with a subscript T. This is the radiant power transmitted by sample. Next term is absorbance, denoted by capital A. It's also called optical density capital D or extinction capital E. These are less frequently used term. Very commonly used is the term absorbance. It can be found by log PO by P or log IO by I. That gives you the absorbance. Transmittance, that is denoted by capital T, may also be called transmission, also denoted by capital T. Commonly, it's called transmittance. It is P by PO, or you could say I by IO, or IT by IO. Next, you have the term path length of sample. So that is designated by small b. It could also have alternative symbols, small l and small d. This is small l and small d. This is the length over which attenuation occurs, or length over which absorption occurs, so far as absorption spectroscopy is concerned. Then you have the next term, absorptivity. We saw it. It is denoted by small a. It could also be called the extinction coefficient, denoted by small k. So small a is actually equal to capital A by BC. And the last term is molar absorptivity, denoted by epsilon. And this is equal to A by BC. Again, the same thing, but I'll tell you what's the difference. The alternate name is molar extinction coefficient or molar absorption coefficient. These are the alternate names. Then what's the difference between A and epsilon? It is in the C value. C in absorptivity represents concentration in grams per liter, whereas C in molar absorptivity is the concentration in moles per liter. That's the difference between absorbance and molar absorptivity. Various spectroscopic techniques. You can see here the type of energy transfer. If it is absorption spectroscopy, then the region of electromagnetic spectrum that is used. You could have so many types of absorption spectroscopy and the name of the spectroscopic technique. So starting at the most energetic side of the electromagnetic spectrum, you used to have the gamma rays, which has absorption of these gamma rays leads to the technique of Mossbauer spectroscopy. Absorption of X-rays gives rise to the X-ray absorption spectroscopy. Absorption of UV visible radiations gives rise to UV visible spectroscopy, one technique, or atomic absorption spectroscopy, a second technique. Absorption of infrared radiation leads to infrared spectroscopy, first technique, second technique being Raman spectroscopy. Absorption of microwave radiation may lead to either microwave spectroscopy or electron spin resonance spectroscopy. And absorption of radio waves leads to the technique of nuclear magnetic resonance spectroscopy. Then you have emission, thermal excitation leading to emission. So if it is in the region of UV visible, then it could lead to atomic emission spectroscopy. And if you have energy transfer results in photoluminescence, that is, the excitation is resulting in emission of excitation by electromagnetic radiation, resulting in release of energy or relaxation by emitting electromagnetic radiation, that's photoluminescence. If it is dealing with X-ray radiations, then we have X-ray fluorescence spectroscopy. And if it deals with UV visible radiations, it could be either fluorescence spectroscopy or phosphorescence spectroscopy or atomic fluorescence spectroscopy. So these are a number of spectroscopic techniques which we can have at different regions of the electromagnetic spectrum. Other spectroscopic techniques, the electromagnetic radiation may undergo a change in amplitude, phase angle, polarization, or direction of propagation as a result of its refraction, reflection, scattering, diffraction, or dispersion by the sample. So if you're dealing with X-rays, diffraction leads to X-ray diffraction. You have this in your syllabus. If you're dealing with UV visible radiation and the type of interaction is refraction, you have refractometry. If the type of interaction is scattering, you have nephelometry or turbidimetry, two different techniques. And if you have dispersion occurring, then you have optical rotatory dispersion. So these are some other techniques other than absorption and emission type of transfers of energy. So